Okay, so we're going to be talking about inference for means here, but let's do a quick review problem. So in 1996, 20% of the students at a major university had an overall GPA of 3.5. In 2000, a random sample of 1,100 student records found that 25% have a GPA of 3.5 or higher. So is this evidence of grade inflation? So we're doing inference for proportions here, right? And if you are following along, you should pause the video right now and work this problem out, and I'm going to go over the solution. So first thing we should do is check some conditions. So if we look at the independence assumption, we could say that student GPAs are presumably independent. The problem states that this was a random sample. 10% condition is covered, so we're sure that we're staying independent here because we haven't oversampled at this university. So 10% means that the university population is 11,000 or greater. That's believable for a lot of universities. And the success failure condition now. So if you go ahead and calculate these, 1,100 times P is greater than 10, and so is NQ. Okay, so the conditions for inference are met here. Now let's take a look at our hypotheses. So the null hypothesis is that the population proportion has not changed. It's still the same as it was in 1996. And the alternative is that it's now larger. Okay, and that's what we're trying to test. That's what we're looking for. Okay, so what we want to do is we want to look at the center of the sampling distribution for proportions here, and that's just going to be equal to that 20%. And we also need the standard deviation, and we can use these to apply a normal model. All right, so we apply the normal model here by going and calculating a z-score based on this stuff. We've got our observed minus our expected divided by the standard deviation we just found. And we find a p-value for z greater than 4.13 of this very small number here. Now let me show you how to do this on the TI calculator. Okay, so we're looking at p greater than 4.13. If we look at the normal model, that means we're way over here at 4.13, and we're looking for the area under the curve greater than that. So visually, just looking at this picture, we can tell that it's going to be a small number, but let's go ahead and calculate it anyways for the sake of practice. So let's come in here to distributions, and we want to do normal CDF, okay? And so my lower bound right here, if I'm going from 4.13 and above, my lower bound is 4.13, my upper bound is positive infinity. So lower 4.13, the upper bound positive infinity. Well, we don't have an infinity button on the calculator, but for all intents and purposes, 100 standard deviations above the mean is just as good as infinity, really. Okay. Now your calculator might not look like this. Yours is probably going to just show the normal CDF like this, and then you put your lower bound, you put your upper bound, and then you put your mean and standard deviation. Now these last two options are optional. You don't have to put those there, and in fact the default values are 0 and 1. So if I wanted to, I could just delete 0 and 1 right here. You could enter this on your calculator, normal CDF from 4.13 to 100, and you get an area under the curve. You might say, wait a second, that's not a small number, 1.8. Well, actually it is, because it's times 10 to the negative fifth. So in other words, 0.000018. I think that should do it. Yeah, okay, that's 1.8 times 10 to the negative fifth. And that's what we're looking at right here. Okay, so what does this mean? How do we interpret it? Well, with a p-value of this really small number, we conclude that it's highly unlikely to observe a p-hat of 0.25 if the true proportion were 20%. So thus, we reject the null hypothesis that the true proportion is 20%. There's a strong evidence to suggest that the proportion of students with GPAs of 3.5 or above is much higher in 2000. Okay? So that was inference for proportions. And now we're talking about inference for means. And this is actually going to look really similar. It's going to be pretty familiar. So the approach is going to be the same. We'll need to look at the sampling distribution of means and find a p-value. Okay? And then based on that p-value, we'll decide whether or not to reject the null hypothesis. So, for the center of our sampling distribution, we'll use the expected value defined in our null hypothesis. And this is what a null hypothesis always does, right? Is it defines some population parameter. It says p is equal to this, or mu is equal to this. So this will be sometimes given for the population, or maybe it'll be based on historical observations in some cases, or something else. It really depends on the context. Now, recall that the central limit theorem tells us that the standard deviation for the sampling mean is given by this equation right here. On the bottom, we've got the square root of the sample size, and on the top, we've got the population standard deviation. How are we supposed to know sigma for the population, right? In real life, this is not given to us very often, okay? So that's what we're looking at really in this chapter, is how do we handle this? And the answer is with this thing called student's T model. So think back to what we were doing with proportions. We could calculate the standard deviation of sample proportions with this thing right here. And note that the equation does not involve sigma. It does, however, involve this p right here. This is the population proportion. So it still required us to know something about the population. But remember, we still figured this out when we didn't have p. We calculated something called standard error. We estimated the sampling standard deviation using the sample proportion. And we gave it a different name, standard error, for that reason. And we can estimate the standard deviation for y bar using the sample standard deviation S. Now, if you don't remember what this sample standard deviation is, remember when we were doing one var stats, and that will jog your memory. Let's take a look at a list here. So I've got a list of data points in L1 in my calculator, and I can go to stat calc one var stats, and this is going to do a bunch of calculations for me, right? I've got my quartiles down here, but if I come back up, I've got my sample mean right there, x bar. I've got my sample standard deviation and my population standard deviation. Now, if all those values in L1 comprised an entire population, this is the standard deviation I'd be going with. Since it's a sample, I would be looking at this one right here. This is the sample standard deviation, and that's what you would put right there in this equation. Okay, so there's a problem here. The problem is that the normal model is not accurate when we estimate the standard deviation of sample means this way. Okay, that means we can't use the normal model anymore. Our tried and true normal model is no longer going to be our go-to tool. We got to use something else. But don't worry, it's not too bad. It's called student's T model. If you want to know why it's called student's T model when it was in fact invented by this guy named Gossett, you should read that section in the book, and it has to do with the beer company that he was working for. Now, whereas heretofore, in order to apply a normal model, we could calculate a z-score for the distribution of sampling means thusly. I'm just trying to say here that hopefully this is familiar to you. We can calculate t-values in pretty much the same way. So it's got different names, but the mechanics are all going to be the same. Now, the only reason that this is mu naught and not a mu is because this is usually going to be a hypothesized value. This is from our null hypothesis. I'm just emphasizing that, but you can be loose with that notation there. So confidence intervals also look very much the same. Remember I told you that a confidence interval is always going to be an estimate plus or minus some margin of error. Okay, so for the one proportion z intervals, it looked like this. We did, our estimate was p hat plus or minus some critical value times the standard error. Okay, well, it's going to look very similar for means. Now, what do you suspect the estimate is when we're talking about means? Hopefully you said y bar, and this is called the one sample t interval for population means. Now, take a look at this critical value right here, t star with a subscript of n minus 1. Let's talk about what that means. So, this t value above is called a critical value, just like z star before, but what's the n minus 1 about? That represents something known as the degrees of freedom. And degrees of freedom is always one less than the sample size. So the T model is based on the number of degrees of freedom. This T model changes depending on your sample size. The normal model did not change with our sample size. So whatever our sample size was, if we satisfied the conditions, then we just went with the normal model, and it was the same normal model every time. But this model, this T model, changes with sample size, and that's why we're always going to go to technology to calculate these values instead of keeping around tons of tables. Now let's just take a look for fun at the T model on something called Desmos. Okay, Desmos T distribution, that works. Okay, so if we look at this picture right here, in the red we've got our familiar normal model, and in the blue we've got a T distribution. Now what do you notice? The T model is still unimodal and symmetric. It looks a lot like a normal model, and N right here is representing the sample size for this T model, and you'll notice as N increases, that blue looks more and more like the red. Okay, I get up to 100 and it's hard to even see a difference, although there is a small difference. If we come back to a very small sample size, you'll notice that the tails are much thicker out here, and that's the main difference really. So what does that mean for us? Okay, well, as we just looked at, when N increases, it looks more and more like the normal model. So in fact, it's equal to the normal model when N goes to infinity. Now, the whole point of doing statistics is to avoid sample sizes like this, to avoid doing censuses, right? We want to just take a sample and try to understand as much as we can about the population from that sample. Now, the last thing that I'm going to reiterate here is that this critical value is based on the confidence level and the degrees of freedom. Okay, so let's do an example. Let's find the critical value T for a 90% confidence interval with 17 degrees of freedom. Okay, so we're going to go to the calculator for this. If my confidence level is 90%, then what area under the curve am I looking for? Well, I'm looking for the 95th percentile. I'm looking for 95.95. Okay, let's take a look at how to do this on the calculator. Okay, so I'm going to go back to distributions right here, and need to ask yourself each time you're doing one of these, are you looking for an area or are you looking for a T value? I'm looking for a T value, so I need to go to inverse T here. This is going to take me from an area to a T value. So I go to 4, and the area that I'm looking for is, we said 95%, right, for a 90% confidence interval. So I'm going to put 0.95 in there for my area. The degrees of freedom, we had 17. Okay, now on your calculator it's going to look like inverse T of 0.95 comma 17, and you hit that, and there's our critical value. Okay, easy as that. That's what we got. All right, now different problem, find the p value for T greater than 2.09 with 4 degrees of freedom. Okay, so now this p-value, that's an area under the curve, right? And I've been given T. So my interval is T greater than 2.09. So if I come back to these distributions, now I'm going to go for TCDF. This stands for cumulative density function. Now if you are studying any calculus at this time, you should associate cumulative density with an integral, and hopefully that'll help you remember that the CDF is giving you the area under this curve. So it's asking me for a lower and an upper bound, and then the degrees of freedom. Now, this is not a normal model right here, but it kind of looks like one, or sorry, this is a normal model. It's not a T model, but they look almost the same anyways. Now, the lower bound here, if we think about what we're being asked to do, we want T greater than 2.09. So 2.09 is somewhere around here, and I want T greater than that. So that means that my lower bound is 2.09, and my upper bound is infinity. But once again, calculator does not have an infinity button. Let's just say 100 standard errors above the mean, and that should be good enough. The degrees of freedom here, we only have 4 degrees of freedom. And so we put that in there. Now, once again, on your calculator, you'll probably just end up with something that looks like that, TCDF of those parameters. Hit enter, and we get a p-value of 0.052-ish. Okay, hopefully that's what I put in my slideshow. There it is. So that's finding critical values, that's finding p-values. Hopefully that sets you on your way with that part. Let's do another example. So in 1882, Michelson measured the speed of light. This is the famous Michelson-Morley experiment. His values are in kilometers per second and have 299,000 subtracted from each one of them. He reported the results of 23 trials with a mean of that and a standard deviation of that. So, what are we going to do with this? Well, let's find a 95% confidence interval for the true speed of light from these statistics. Now, whenever you're doing these problems, you should just start by writing down what's been given to you. So let's just write down all of these numbers with their proper names. Okay, so we've been given a sample mean from his 23 trials, and we also have the sample standard deviation. Okay, so where are we going to go with these things? Well, let's find this confidence interval. So let's start by looking at the standard error. The standard error is the sample standard deviation over the square root of n. I get this number right here. Okay, and this critical value t is given by that. So I'm gonna do this again for you real quick. Let's take a look at how you would find that t value. Okay, so it's a 95% confidence interval, right, for the true speed of light. So 95% confidence means that we should be looking for an area of 97.5. Okay, so I'm going to come back here to my distributions, and I'm going from an area to a t value. So I'm looking for t value. I need to use this inverse function here. The area was 97.5, and the degrees of freedom, well, degrees of freedom are n minus 1, so I've got 22 degrees of freedom in this case. Okay, that's what's going into my calculator. Uh-oh, what happened? Okay, well, this 97.5 right here, that meant 97.5%, right? So I need to change this to 0.975. And now I should be cooking with gas. So we get 2.07387-ish for that critical value. Okay, good. Now, what are we going to do with it? Well, all we have to do now is just plug it in and find the interval. Okay, this means our observed y bar right here, plus or minus this product. Okay, those are the two values I just found. And I get an interval of 709-ish to 802-ish. Okay, so let's interpret this. Okay, here's my problem again. Here's my context. Here's my interval. Now remember, they said that each of those values had 299,000 subtracted from them. So I'm going to go ahead and add them back here, and there they are. And what does this mean? This means that I'm 95% confident the true speed of light is somewhere between 299,709.9 kilometers per second and 299,802.6 kilometers per second. Okay, this is the correct way to interpret a confidence interval. Now, let's do a different example. In 1960, census results indicated the age at which American men first married had a mean of 23.3 years. It's widely suspected that young people today are waiting longer to get married. We want to find out if the mean age of first marriage has increased during the past 40 years. So what could we do? Well, let's take a sample of 40 men who married for the first time last year and be a random sample. The mean and standard deviation of that sample were 24.2 and 5.3 respectively. Okay, so let's do some inference. Okay, let's start out with just stating our hypotheses. So my null hypothesis is that mu hasn't changed since 1960. Okay, the average age in 1960 was 23.3 years, and so that's my default. That's my go-to value for the null. What's the alternative here? Well, we're asking the question: has it increased? Is it larger? And our sample shows that it's a little bit larger. So now we're going to do, we're going to find a p-value and see, is this statistically significant? Okay, so first though, we should check some conditions, and here's what the conditions look like for inference about means. So we can assume that the age at which one man marries is independent of other men. Or can we? I don't know. I kind of feel like these decisions, I feel like people base these decisions kind of on society's general attitudes about these things. So I'm just going to say that right here, and I'm going to proceed anyways. The problem told us this was a random sample. 40 men is certainly less than 10% of all recently married men. And we want to make sure that our data, they're nearly normal. Okay? But if you think about this problem, these data are likely skewed right. Because if you think about it, people who get married young probably don't get married younger than 18, for example. Very, very, very few men are going to get married younger than the age of 18. And so that kind of puts a hard limit on the left-hand side there. But what we're talking about is that some men are getting married older and older. So some men getting married in their late 20s, on into their 30s, or even later. So it can kind of get dragged out to the right there. So these data are likely skewed right. Now, we're going to be pretty safe if our sample size is large enough. N equals 40 is not that big, but it's not that small either. So we're just going to say it's large enough. It won't be too problematic, but we'll proceed cautiously. Okay, so let's restate what we know about this problem. We've got our hypotheses, we've got our sample size, sample mean, and standard deviation. Okay, so we're going to apply students' t-model with 39 degrees of freedom, right? 40 minus 1 is 39. Okay, the standard error of y bar is going to be given by this. We've got our 5.3 taken from the sample standard deviation. We've got our sample size down here. And let's take a look at this again. This is just like the way we were calculating z-scores before. So how do we find this t-value? We took our observed value and we subtracted the expected value. Then we divided that by the standard error that we just found, and I get a t-value of that. Okay, so where do we go from here? Well, there's my t-value. I need to find a p-value. Okay, so the probability of making this observation right here is given by that. And let's just do it on the calculator one more time. So I've got, I want to look at this distribution. I'm looking at t-CDF. And my lower bound, okay, I'm looking for t greater than this. So that is going to be my lower bound, 1.07, what was that? 40. My upper bound is infinity, so 100 should be plenty good. You could probably get away with 10 right here, but this is extra safe. How many degrees of freedom? It was 39 for this problem, okay? And we stick that in the calculadora. And boom, there's my p-value. Okay, same one I got right there. Good. Now, what do we do with that? Well, with a p-value of 0.1447, that means that about 14.5% of the time, I could make this observation right here if this is the true mean. Okay. Now, 14.5% is substantial. That's you know, that could happen. So there's no evidence telling us that we should reject the null hypothesis here. And there's no evidence to suggest that the average age of men at first marriage has significantly increased since 1960. Okay, so here's how you can blow it. Okay, you can confuse proportions and means. Okay, so don't start applying these techniques when you should be working with population proportions. How else can you blow it? Well, you could use the t-model when you've been given sigma. Okay, so the t-model is only when you don't have sigma. If you've been given sigma, go ahead and use z-scores in the normal model. That's what the central limit was for, and we can definitely use all that stuff. So just use students' t-model when you don't have sigma. Okay, how else could you blow it? Well, you could apply the t-model to multimodal data. Okay, that would be a big mistake. Our data has to be nearly normal. That means the sample has to be nearly normal. When you look at that sample, is it nearly normal? And you should be thinking about the population too. If you're looking at a co-ed population where there's men and women in your population and you're measuring something about the two that is expected to be different for men and women, you should probably consider splitting them up into two groups. Okay? Well, how else could you blow it? You could apply the t-model to very skewed data. Now, you can get away with this when your sample size is very large, but just think about it, be cautious. And state something. When you're working these problems, state it when you go to check the condition, so you look like you know what you're talking about. At least you check the condition, and you know that you should be cautious with results if the data are skewed. Okay? You can also blow it by applying these methods with outliers in your data. If there are outliers in your data, that could significantly change your results. So the best approach is to look at your sample mean and your sample standard deviation with and without the outliers. Okay? If there's not a large difference, then it doesn't matter that much. If there is a big difference, you should do your calculations separately and state your final results. Okay? You can also blow it by applying these methods to biased data. So if we're thinking about that Michelson-Morley experiment, if there was something about their experiment like built in, where there was some kind of error built into their experiment where the speed of light was going to be constantly overestimated by 1,000 kilometers per hour or something, that's called bias. So think about the problem. Is there bias? Now, you can also blow it by applying these methods when the cases are not independent. So go ahead, check that every time, think about it. Sometimes you're going to say, well, these might not be independent, but for the purpose of this calculation, I'm just going to assume they are. Sometimes you just do that, okay? Well, another way to blow it is to apply these methods when the samples were not done randomly, okay? It's very important to be working with random samples in order to balance out any kind of bias or any kind of other factors in our population that we can't control for. And the final way that you could blow it is you could interpret your confidence interval in a foolish way. And the book gives us lots of examples for how to foolishly interpret a confidence interval. I gave you one example where I correctly interpreted the confidence interval. Go back, read some of those bad examples in the book so that you don't act like a fool. Well, boys and girls, I hope you enjoyed this. Play safe.